Hello and welcome back to Chopstick Maths. In this video, we shall be solving sum number 6 from exercise 3. We will be solving the given differential equation x raised to 4 into e raised to x minus 2mxy square dx plus 2mx square y dy equals to 0, where m is some constant. And let us call this as equation number 1. Now we'll have to first find out if this given differential equation is an exact differential equation or not. So let us compare this given differential equation with m dx plus n dy equal to 0. And on comparing, we get m equals to x raised to 4 into e raised to x minus 2m xy square and n equals to 2m x square y. Now we'll have to differentiate m partially with respect to y and differentiate n partially with respect to x. And if del m by del y equals to del n by del x, then we can say that the given differential equation is an exact differential equation. So now let us proceed ahead to differentiate m partially with respect to y. So del m by del y equals to del by del y of x raised to 4 into e raised to x minus. Now whenever you are differentiating partially with respect to y, you have to treat x as a constant. Now this m is also a constant, therefore minus 2mx comes outside, so this is minus 2mx del by del y of y square. Now since we are treating x as a constant as we are partially differentiating with respect to y, del by del y of x raised to 4 into e raised to x equals to 0. And del by del y of y square is 2y. So del m by del y equals to 0 minus 2mx into 2y. So del m by del y equals to minus 4mxy. Now, let us differentiate n partially with respect to x. Therefore, del n by del x equals to 2my del by del x of x square. Now, whenever you are differentiating partially with respect to x, we have to treat y as a constant. And m is also some constant. So, therefore, 2my will come outside. So, del n by del x will be equal to 2my del by del x of x square. Now del by del x of x square is equal to 2x. So del n by del x will be equal to 2my into 2x. Therefore del n by del x will be equal to 4mxy. Now del n by del y is not equal to del n by del x. Therefore this given equation is not an exact differential equation. Now we'll have to find a suitable integrating factor such that when we multiply this given differential equation with that integrating factor, this given differential equation will be reduced to an exact differential equation. Now if del m by del y minus del n by del x upon n is a function of x only, say f of x, then the integrating factor is equal to e raised to integral f of x dx. Now del m by del y equals to minus 4 mxy and del n by del x equals to 4 mxy. Therefore, del m by del y minus del n by del x upon n equals to minus 4 mxy minus 4 mxy upon n is equal to 2 mx square y. So this would be equal to minus 8 mxy upon 2 mx square y. Now here the m and m would cancel out in the numerator and denominator. The y and y would cancel out in the numerator and denominator, and the x term in the numerator and denominator will cancel out. So what will remain is minus 4 by x. Therefore, del m by del y minus del n by del x upon n equals to minus 4 by x. And this is a function of x only. And let's call it as f of x. Therefore, the integrating factor is e raised to integral f of x dx. Now, let us substitute f of x, which is equal to minus 4 by x. So the integrating factor would be e raised to integral minus 4 by x dx. Now minus 4 is a constant and we can pull it outside the integral sign. So this would be e raised to minus 4 integral 1 upon x dx. The integral of 1 upon x dx is log x to the base e. So the integrating factor would be e raised to minus 4 log x to the base e. Now we can simplify this integrating factor by using the property of logarithm. M log a to the base e is equal to log a raised to m to the base e. So we can write this integrating factor now as e raised to log x raised to minus 4 to the base e. Now still we can further simplify this integrating factor by using another property of logarithm, which says that e raised to log f of x to the base e is equal to f of x. Therefore, by using this property, we can write this integrating factor e raised to log x raised to minus 4 to the base e as x raised to minus 4. So the integrating factor is equal to x raised to minus 4, which can be now written as 1 upon x raised to 4. Now, on multiplying equation 1 by the integrating factor 1 upon x raised to 4, we get 1 upon x raised to 4 into x raised to 4 into e raised to x minus 2m xy square dx plus 1 upon x raised to 4 into 2m x square y dy is equal to 0. Now, this would be x raised to 4 into e raised to x upon x raised to 4 minus 2m xy square upon x raised to 4 dx plus 2m x square y upon x raised to 4 dy is equal to 0. Now, x raised to 4 will cancel out each other in the numerator and denominator, and what would be left is e raised to x minus, here x will cancel out each other in the numerator and the denominator, and what would be left behind is minus 2my square upon x cube dx plus, here x square would cancel out each other in the numerator and the denominator, and what would be left behind would be 2my upon x square dy is equal to 0. And let us call this as equation 2. Equation 2 is an exact differential equation, and the solution to the exact differential equation is integral m dx keeping y as constant plus integral n dy integrating only those terms in n which are free of x equal to some constant c. Now, n is equal to e raised to x minus 2my square upon x cube. We'll have to integrate m with respect to x, treating y as a constant. So the first term is e raised to x, so this would be integral of e raised to x dx minus, now the second term here m is some constant and we'll have to treat y square as a constant. So minus 2my square will be a constant and we'll have to write it outside the integral sign. So this would be minus 2my square integral dx upon x cube plus, now we'll have to integrate only those terms in n which are free of x. Now here n has just one term 2my upon x square, and as per the rule we'll have to integrate only those terms in n which are free of x, and if you can see over here there is an x square in the denominator, so we'll have to neglect this term. So we'll have to write it as plus integral 0 dy is equal to some constant c. Now we can write this as integral e raised to x dx minus 2my square integral of x raised to minus 3 dx is equal to c. Now integral of e raised to x dx is equal to e raised to x, and integral of x raised to minus 3 dx, this can be integrated using this formula. Integral of x raised to n dx is equal to x raised to n plus 1 upon n plus 1 plus c. Therefore, integral of x raised to minus 3 dx will be x raised to minus 2 upon minus 2. So this would be minus 2my square x raised to minus 2 upon minus 2 is equal to c. Now this would be e raised to x, and this minus 2 in the numerator and minus 2 in the denominator would make the second term positive. So this would be plus my square upon x square, as 2 would cancel out each other in the numerator and denominator, and that would be equal to c. Now taking the LCM, we can write this as x square into e raised to x plus my square upon x square is equal to c. And finally we can write this as x square into e raised to x plus my square equal to cx square. And this is the solution to the given differential equation. Thank you very much for watching the video, and if you have liked the video, please do consider subscribing to the channel. See you in the next video. Bye for now.